Welcome to EDU World Space.
Another version of the Heisenberg uncertainty principle allows us to calculate the line width in a particular spectrum. By line width, we mean that ordinarily when you're looking at a spectrum, so the intensity versus wavelength, there will be an emission line that happens at a particular wavelength. And usually these are not very narrow lines. They have some sort of width associated with them. And one of the sources of that width is uncertainty in the energy, of course, of the photon coming out. And that uncertainty in energy is related to the lifetime of the state, the amount of time that the electron spends being excited through uncertainty in energy times the uncertainty in the time of existence is of the order of h bar. So it looks very much like the position momentum form. And we can see that energy times time certainly has the units of h, or h bar. Okay, so what we're told, we're looking at the first excited state in hydrogen falling down to the ground state. And we would like to find the uncertainty in the wavelength. And the way to do that is, of course, start off with the energy. And this is the uncertainty in the wavelength of the emitted photon. So be clear about that. Whereas the uncertainty in the time is the uncertainty in the lifetime of the electron hanging out in that state. But we'll start with the energy expression for a photon in terms of wavelength. And we can take the derivative of that with respect to lambda. Bear with me. And we can kind of recast that as minus energy over lambda. And now we can think of those infinitesimal differences as uncertainties and separate delta E photon. We're going to take an absolute value too, because it's an uncertainty. So it really is a plus minus. Okay, so now let's kind of work through the details. What we're told is for this particular state, delta t is 10 to the minus 8 seconds. So it exists in that state for roughly 10 nanoseconds. So from the uncertainty principle, we can calculate the uncertainty in the energy is essentially just h bar over delta t. And of course, that is, I'm going to use my atomic units. H is 4.14 times 10 to the minus 15 eV seconds. It's divided by 2 pi. And the uncertainty in the lifetime. And that gives us a very tiny fraction, 6.6 times 10 to the minus 8 eV. Now for the rest of this, notice that we need both the energy and the wavelength of this transition. And of course, what we're using is the energy of the photon and the wavelength of the photon. So the energy of the photon is simply 13.6 electron volts times 1 over 1 squared minus 1 over 2 squared. And that's easy, 10.2 electron volts. And we can find the wavelength. Again, using our atomic units. And we get about 122 nanometers. So now we can put all that together. We'll have to cross multiply, but delta lambda is equal to delta E photon times lambda over energy. So very small uncertainty in electron volts for the energy, 122 nanometers for the wavelength, and 10.2 electron volts for the energy of the photon. And this still comes out to be a very tiny number. Sometimes this is called the natural line width. And usually the spectrum is smeared out by a lot of other things, including the motion of the atoms causing Doppler shifts and the spectrometer having some sort of limited resolution. So to be able to see the natural line width, you need very carefully controlled experiments and precise spectrometers. Now you can see why.